Good afternoon, I'm Professor Sever, and today we're going to discuss linear independence in our linear algebra course. Thank you for joining me for this video series. So let's consider this problem. We have three vectors. We want to determine whether they are linearly independent. So the first question is, how do we go about making that determination? So what do we need to do? We need to form a matrix using as its columns these three vectors. And by doing so, then we will apply the theorem that says the columns of a matrix are linearly independent if and only if there's a pivot position in each column. That's a fundamental theorem for us in this course. So let's do that and see what we get. So once we form the matrix using these vectors as its columns, we then need to check for a pivot position in each column, again through the process of row reduction. We can't see the pivots until we row reduce the matrix to echelon form. So our plan will be to form a matrix using as its columns these three vectors, row reduce the matrix to echelon form, inspect the columns for pivots, and what we're really looking for is a pivot position in each column. If we have that, then the columns are in fact linearly independent. If we do not have that, then the columns, and hence the original three vectors, would not be linearly independent. Let's begin this process. So the first thing we see is that we need to produce a 1 in the upper left corner in the 1, 1 entry of the matrix. To do this, we use a type 2 elementary row operation, which is we multiply row 1 by negative 1/3. And when doing so, the second and third columns remain the same, and the first column then becomes 1, 0, 0, because 1/3 times negative 1/3 times 0 is 0, and of course negative 1/3 times negative 1 is 1. So now we have a 1 in the upper left corner of the matrix, namely in the 1, 1 entry. Now the next phase is to produce zeros below it. To do that, we need to multiply the first row by negative 4 and add that to row 2. That would put a 0 in the 2, 1 position. Then we need to multiply the first row by negative 2 and add that to row 3. That would place a 0 in the 3, 1 position. When we do this, we obtain the following. In the second row, we get 0, 5, 0. And in the third row, we obtain 0, minus 8, 1. So the first step in our reduction process is complete. We have a pivot in row 1, and we have zeros below it. Now we need the 2, 2 entry to be a 1. We accomplish this by multiplying row 2 by 1/5, and when we do that, you see the second row, the first and third rows remain unchanged because we're not manipulating those rows through our elementary row operations, and we obtain the matrix which has a second row of 0, 1, 0. Now we have a pivot position in row 2, namely in the 2, 2 entry. So now we need to clear out below that entry, namely we need to get zeros below it. Therefore, we need to multiply row 2 by 8 and add that to row 3. When we do that, we will obtain the next step. And of course, in this video, I'm leaving the arithmetic to you. I'm going through the decision-making process that will allow us to obtain the row echelon form. And when we do that, we will see that we obtain the matrix, which is row reduced. And we see it right here. So let's reiterate. The matrix is in fact in echelon form. We detect the pivots. I have them highlighted. Now, do we have a pivot position in each column? The answer is yes. Therefore, we may conclude that the columns are linearly independent. Hence, we have answered the question we were asked. The original three vectors that we were given are in fact linearly independent in R3. This process used the technique of row reduction as the basis for making our determination. Actually, it was the work that produced the echelon form, And inspecting the echelon form allowed us to make the appropriate conclusion because we have a theorem that refers to pivots. And remember, pivots aren't detectable until we achieve the echelon form of the matrix. Now, as a student, when you're doing your work for this type of problem, it's important that you show all the steps of the row reduction, terminating in the matrix that we obtain in echelon form. Remember, that's not unique. We all can obtain a different echelon form. But you would get an echelon form of the matrix. Now, we would all get the same pivots, namely the pivots would be in the same pivot positions. But then you need to make sure you articulate your conclusion. Many professors, we grade students' work, and oftentimes what a critical error is, the student will just not make any conclusion. They'll just terminate the problem, leave the matrix in echelon form, and not state any answer, in fact, to the question whether the original vectors were linearly independent or not. So please remember, once you complete the row reduction, you then need to actually answer the question being asked. Are the vectors linearly independent? And you wouldn't just want to say yes, you need to say why. You need to state that it hinges on the fact that there's a pivot position in each column of the matrix. And by doing so, what you're really doing is you are referring to the appropriate theorem which allows you to draw this conclusion. So again, the work is important. You must do the row reduction, but you also must make the appropriate claims and state why you are able to claim that the columns are linearly independent. Let's think about it. This is a decision problem. It's just a yes or no. So we don't really want to know that the answer is yes. We want to know why the answer is yes. And as a grader, I want to know whether you know why the answer was yes or no. I'm Professor Sever, and thank you for participating in this video on linear independence. Please look forward to my next video in this series. Thank you.